Okay, this is video 15A, starts lesson 15. We're going to get into confidence intervals for proportions. So this picks right up where we left off with chapter 14. And we're going to use one of the examples from lesson 14. So recall that in 2013, Mother Jones magazine had reported that 45% of homes, ready to say guns, of homes in the U.S. contained guns. We'd like to run an investigation to see if Cecil County, if there's any evidence that we differ substantially from that national figure. So we designed a study to unbiasedly sample 400 homes in the county, and we will determine whether or not the homes selected have guns. So same example we looked at before. In lesson 14, we looked at the theoretical normal model of the sample proportion. If we imagine taking many repeated samples, this is the model that we come up with. However, it was based on a very critical assumption. We assumed right from the beginning that 45% national figure that came from Mother Jones magazine was the same in Cecil County. So all of that normal model, that picture that we drew, it was centered at 45%. It was all based on the assumption that in Cecil County, 45% of the homes contain a gun. So just to recall here, this was based on a crucial assumption. We assumed P was 0.045 or 45% for Cecil County. Okay, so what if in Cecil County we would like to estimate the proportion of homes that have guns? How would we go about this? Back in 14, when we were looking at the model for sample proportions, we made this assumption. Would we actually know this, like starting out with a problem? Do you know? Like, is this just a fact that we know that 45% of Cecil County homes have guns? We don't know that. We don't know what the proportion is. So in Cecil County, if we'd like to estimate the proportion of homes with guns, what would we do? We'd take a sample of homes. Well, let's say that when we take a sample of homes, that it turns out that 300 homes out of the 400 have guns. Now, we just completely made this up. We never sampled 400 homes. This is just a figure that we've come up with. But if we had to give our best guess, if we did this, and 300 out of 400 homes had a gun, and then we want to use our sample data to come up with the best guess for gun ownership in Cecil County, what would it be? We'd use our data, right? Our best guess would be this figure. We know if we did it again, it wouldn't be exactly 300. It's probably going to be a different value. But for now, with this sample here, that would be our best guess. So we'll use our data. Best guess would be our sample proportion of 300 out of 400 homes, or 75%, quite different from that national figure. So this is our best guess. It is our best guess, but we do have to keep in the back of our mind that every time you sample, you're not going to get the same figures, that those sample proportions will vary from sample to sample to sample. So we keep that in the back of our mind here. All right, let's see what's next here. All right, we'd like to do better than a single best guess, in part because I know if I did it again, I'd get a different number. So in lesson 15, rather than giving a single best guess, we're going to look at a range of values, and that range of values, range of plausible values, range of values that could happen. That range of values is called a confidence interval. And so we're going to use the ideas that we learned back in chapter 14 about the distribution of those sample proportions to construct and to build what are called confidence intervals, a range of values. Instead of saying it's 75% gun ownership, we might estimate that it's somewhere between 70 and 80% gun ownership. So we'll see where this leads. Confidence intervals. So all of lesson 15 is about constructing confidence intervals for proportion problems. All right, so let's keep going. D. All right, we know that in Cecil County, the proportion of homes with guns will also follow a normal model if we took repeated samples. And that p hat of 0.75 is probably not the center of that normal model. We know if we did this over and over again, we're going to get different numbers there. And so in Cecil County, we're actually working with a normal model where, I don't know where that's going to be centered. We don't know what where the mean is. We have a guess here, but I know if I did that again, I'd get a different guess. So we don't know the center. We don't know the mean. So we're working with a normal model with an unknown mean. This is sort of the first time we've been in this situation. If we took another sample, surely we would get 300 gun owners again. We might get 290 out of 400, or you might get 350 out of 400, but certainly that figure would probably change. So this is our best guess based on the data that we did collect, but we don't know the true center of that normal model. All right, so we don't know where the true center is. So where should we center our normal model for gun ownership in Cecil County? We're going to use our best guess. We're going to go with the data told us, right? And so we're going to center our model at the sample proportion that we got from our sample of 0.75. So use the data you collected. Keeping in the back of your mind, if you did this again, all right, this would probably be a different number. That's okay. Oops. Center our normal model at that best guess. We're going to center it here. We're going to center it here, but we're going to come up with an interval of values that will kind of take into account that, okay, this could vary if we did this again. Okay, that's where we'll center our normal model. Remember, to use the normal model, you need a center, a mean. You also need something about the spread. So what are we going to do about that? So when working with the normal model, we also need a measure of spread. Since we do not know the true proportion of gun ownership in Cecil County, we can't obtain the standard deviation of the normal model like we did before. Oh, we've got a blank here. So before, when we assumed that we knew the population proportion, we had this formula for the standard deviation. But if you don't know the population proportion, you're not able to compute that. So this is unknown. So we don't know the true center of our model. We don't know the true standard deviation of our model. But again, we're going to use the same solution that we used for where to center this as we are for the spread. Our solution is use that data you collected. So we're going to use the collected data along with the sample proportion we got from that. And we're going to estimate a measure of spread. Oops, and we're going to go to the next slide to write down the formula. I was going to try to squeeze it here, but I see I've got more room. So we'll estimate that on the next slide. That's good. All right, so we know our sample proportion from our data. We're going to use this value. We're going to use this to make an estimate of the spread, but using sample information. And that estimate we're going to use is the standard error instead of the standard deviation. And so I'm not sure that we've seen this yet. Can't spell today. Standard error. So what will the standard error of the sample proportion look like? It's going to look a lot like the standard deviation, only when we don't have the population proportion, we're going to estimate that with the sample proportion. So for the standard deviation, we had the square root of p times 1 minus p over n. When we look at the standard error, we don't know what these population proportions are, so we estimate those using our data, using those sample proportions. We can go ahead and compute that for this problem. So our sample proportion is 0.75. And this was based on a sample of 400 homes. And if you plug that in your calculator, you'll find out that this is about 0.0217. We could also express that as a percentage. That's about 2.17%. So this is what we're going to use to estimate the spread in our model. So we've talked about where it's going to be centered. We've talked about the spread. Pay attention here. Got to keep focused. What's this say? We're trying to come up. Yeah, what's the whole point of where we're going with this here? We're trying to come up with a range of plausible values for the rate of gun ownership in Cecil County. Our best guess is 75%. Now we have an estimate for spread, which is about 2.17%. We also know for sample proportions, a normal model applies. All right, let's put all this together. We wanted to come up with a range of values. So let's use some normal model theory to build what's called a confidence interval. Instead of saying we think it's 75% in the county, let's get a range of values. And this is going to be completely based on things that we've learned about with the normal model. So recall for just a second, remember the empirical rule. We've drawn this up here a bunch of times, that if we look at our samples, about 68% of our samples will produce a sample proportion that will fall within one standard error of the true proportion of gun owners in Cecil County. So I'll say about. These aren't exact. So close to 68% of the samples will fall within one standard error. About 95% of our samples will produce a sample proportion that's going to fall within two standard errors of the true proportion. And almost all of the samples, 99.7% of samples, will produce a sample proportion that falls within three standard errors of the true proportion. All right, so let's use this. And again, we've kind of lived by this, but these aren't exact. I'm going to kind of focus on the second one, within two standard errors. About 95% of the time, excuse me, our samples will produce a sample proportion that's within two standard errors of the true proportion. So we're going to focus on that one for a minute. So in practice, we're going to focus on 95. 95% confidence intervals are pretty common. You'll construct a lot of these. So let's build a 95% confidence interval for the true proportion of gun owners in Cecil County, completely based on what we just had up here. So what's our best guess? Just had it up here. About 95% of the time, we're going to get a sample proportion that's within two standard errors of that center value. So we're going to take, to build a confidence interval, you're going to start with your best guess. I'll write down our best guess in a minute. That was from the sample, right? And then, okay, I know if I did this again, I'd get a different value, but I also know that these values follow a nice normal curve. And so I'm going to add and subtract a little bit to this. If I want to be 95% confident, I'm going to go out two standard errors from that best guess. Okay, so in symbols, our best guess was p hat, the sample proportion. I can leave this as standard errors. And we know what these values are. Our best guess from our sample was 0.75. And then we're going to add and subtract from that value 2 standard errors. And we just computed the standard error was about 2.17%. But as a decimal, it was 0.0217. And so rather than just saying this best guess, when we add and subtract, we're going to get an interval of values. So go ahead and do this part first. What do we get over there? 0.0434. And now we're going to write these in order. I'm going to write the smaller value to the left and the larger value to the, whoops, saying that backwards. Nope, smaller value to the left, the larger value over to the right. I'm going to take 0.75 and subtract 0.0434. That'll give me sort of the lower limit of this confidence interval. And then I'm going to take 0.75 and add this 0.0434. I'm getting tongue-tied today. Okay, so when you do that, I trust you can put that in your calculator. Use the right numbers, not the ones that were coming out of my mouth there. For the lower bound, 0.7066, and when I add, you'll get 0.7934. You always want to write the smaller number down here. Think of this like a number line. So smaller number, here's the bigger number. With proportion problems, most of the time we'll convert these to percentages because it just makes sense to think about them as percentages more. So between 70.66% and 79.34%. Both of these, this is our confidence interval. So we're estimating the percentage of gun owners in the county not to be 75%, but to be somewhere in this range of plausible values. So that's constructing the confidence interval. It's really completely based on the normal model, and that approximately 95% will fall within 2 standard errors of the center there. So we've computed that. Another important part of this will be interpreting your interval. So I think that's what we're going to look at next. And then we'll talk about whether our interval shows some evidence that this contradicts that nationwide figure. So let's get to those. All right, so let's interpret our interval with a sentence. I'm going to use the one in percentage format there. Remember, if we were to do this all over again, we wouldn't get 75% of the homes that would be gun owners. If we did this again, sampled 400 different homes, it might be 72%, right? What this confidence interval gives us is a set of plausible values. If you were to do this over and over and over again and construct confidence intervals like this based on different sample proportion values, 95% of those intervals are going to contain the true population proportion. 5% of them won't. You don't know whether that's one of the ones that does or doesn't. A lot of this is based on probability, but 95%, we feel pretty confident in this. So we are 95% confident that somewhere between 70.66 and 79.34% of all Cecil County homes have guns. We are 95% confident between 70.66% and 79.34% of all homes in Cecil County have a gun. Get rid of that. All right, and then the last thing we'll do with confidence intervals is often, to sort of compare these to that original value that was given. So originally from that magazine, it said that gun ownership nationwide was 45%. Let's compare our interval to that. So does it look like we have compelling statistical evidence that gun ownership rate in Cecil County differs from that national figure? Here's our interval. We estimated it to be somewhere here. Think about where 45% is. Think about your normal model. We went out 2 standard errors. 45% is nowhere even close to this interval, right? It's way, way well below the entire interval. So based on using normal model techniques, it would appear that yes, there is compelling statistical evidence that the gun ownership rate based on this sample here is different than that national figure of 45%. And so we could just make a statement to that effect here. So since this entire interval is well above 45%, we definitely do have rather compelling evidence here too. It's not just a little bit above, it's very far above. That Cecil County differs from the rest of the country or from the nationwide figure. And you can almost imagine, the likelihood of getting a sample like ours and this being true seems pretty small. That's nowhere close to this national figure that was given at the beginning here. So this was the first example where we went through constructing a confidence interval. We're using sample data now, and using that sample data along with the empirical rule for now to sort of estimate a plausible set of values, and then you can compare that plausible set of values to other values to see, if you think there's statistical evidence for certain things. So just a preliminary example to get you thinking about the idea of constructing a confidence interval. Joe Cooper-Stanton will pick up with the next video, and we'll show you lots more examples, I'm sure. Thanks for watching.